The driving question for the Unit 1 test is, what is matter? We know from the worksheets that we've completed, the Eureka videos, discussions, and labs, that matter is made up of two things: mass and volume. Now, you need to be able to define each of these terms. Mass is defined as the amount of stuff, and volume is the amount of space that matter occupies. So all matter contains mass and takes up space. Matter is also made up of particles, which is why we practice drawing particle diagrams. And when you take the test, you should be prepared to draw particle diagrams representing matter in different states. Okay, so whether that means drawing lines to show movement, or drawing the fact that particles may be leaving the system because of they're a gas, or if we're trying to represent a solid, we should draw particles fairly close together, and so it forms a solid arrangement. But particle diagrams are kind of a key piece to the fact that matter is made up of small particles. A very important topic that we also talked about in Unit 1 is density. Density can be defined as mass over volume, where mass is measured in grams and volume is measured either in milliliters or in centimeters cubed. Now, something of note here is when we are looking at milliliters and centimeters, we know that this is a 1-to-1 ratio. And when you did your lab, you may not have gotten a 1-to-1 ratio, but many of you saw something very close to that, where the slope of our line, when we graphed milliliters versus centimeters cubed, was very near a line that looks something like that. So the actual slope of the line gave us a physical meaning, and that was the relationship between those two units of volume. Now also, when we look at density, a graph of mass versus volume, and we would title this graph mass versus volume. A substance that has a density of 1 would have a slope that looks like this. An example of a substance that has a density of 1 would be water. Grams per milliliter. So the slope of this line says that 1 milliliter of water has a mass of 1.0 grams. If a substance were more dense than water, the slope of the line would look something like this. And what we can do here to determine the approximate density is we can choose a mass and trace this line over to both that substance A and water, and we can bring it down to the volume axis. And what we see here is that there is more mass in less volume, which means that A has a higher density than water. On the other hand, if we want to look at a substance that is less dense than water, it would have a slope that looks something like this. And we can do that same thing again to determine the relationship of density between two different substances. We can trace a line over from the mass axis and then down. And what we see here is that it has less mass, or I'm sorry, the same amount of mass, but it takes up more space. So, same amount of mass, more space for substance B means that the density number goes down, and it is therefore less than 1. It is less than water. So this is an example of a density graph and how we would determine the amount of mass there is in a certain volume of a certain substance. Accuracy and precision are also very important topics in Unit 1. When we use different pieces of equipment or tools in the lab, or when we are collecting data and presenting our data to the scientific community, we need to be concerned with the accuracy and precision at which we do such a thing. Accuracy can be defined as how close we are to an accepted value. So if we consider throwing darts, we would always like to be hitting the bullseye on each toss. So the bullseye would be the accepted value that we're shooting for. Precision, on the other hand, is whether our results, or in the case of a dartboard, if our throws are repeatable. So even though we may not hit the bullseye every time, if we can get our throws to all be grouped in a similar location, we would consider to have high precision. So if we were to think about this in terms of a drawing, and we make a rough sketch of a dartboard with our bullseye in the middle, if we were to throw 3 darts at each bullseye, we would have high accuracy and high precision on the left, and low accuracy, high precision on the right. Now obviously, we went over other examples in class, and it is possible to have low accuracy and low precision, and it's also possible to have good accuracy and low precision. If we were to look at pieces of equipment that we would use in the lab, possibly a graduated cylinder or a beaker, we would be concerned with the graduations or the marks that are on each of the tools. Okay, if this is a 100 ml beaker, what does each mark represent? Versus if this were a 10 milliliter graduated cylinder, what does each mark represent? And then are there tiny marks in between that allow us to make more accurate readings? So if I were to put some liquid into our graduated cylinder, we would want to read this from the meniscus, and the meniscus is right down here at the bottom of the volume level, and we ignore the adhesive forces of the liquid with the containers of the graduated cylinder, and we take our reading from there. What we would see is that a tool like a graduated cylinder gives us a more accurate reading because there are more graduations. So if we wanted to have better accuracy in our readings, we would use the tool that has more lines for us. Beakers are better for measuring larger quantities, larger volumes, where we don't need great accuracy. Significant figures are very important in science, and especially physics and chemistry. Significant figures allow us to represent our data with no more preciseness or accuracy than the data that we collected with the certain tools that we collected in a lab. So significant figures include everything or every digit or number, everything that we know and we are certain of, plus it includes one uncertain number. So on the next slide, I'll give you a number of examples of significant figures and talk about some of the rules. Significant figures have certain rules that we need to follow. And so the first is all non-zeros are significant. So in other words, 212 has 3 significant figures. 1.254 has 4 significant figures. All non-zeros are significant. Continuing on with our rules, any zero between non-zeros, between non-zero numbers, is also significant. So a couple of examples. 105 contains 3 sig figs. 2007 contains 4 sig figs. Because the zeros are between non-zeros, therefore they are significant. The next rule states that any zero that is a placeholder is not significant. Any zero that is to the right of a decimal but before any number is not significant. So 0.005 only contains 1 significant figure. 0.0051 contains 2 significant figures, and 0.0050, how many significant figures do you think are in this number? clearly the 5 is a non-zero, so it is. Any 0 to the right of a decimal and to the right of a number is also significant. So the question is, are these 3 zeros before the 5 significant or not? And the answer here is that yes and yes, these two are, but the first 3 are not significant. So this number actually only has 2 significant figures. The final rule is zeros at the end of a number may or may not be significant. Okay, sometimes this is a tricky one for students, so the only thing you really need to be on the lookout for is there a decimal or not? So, a few examples. 1 has 1 sig fig. 10 has also only 1 sig fig. But 10 point, this one has 2 significant figures. And just to do a couple more examples for you, 100 has only 1 sig fig, but 100 point has 3 sig figs. Okay, so the presence of a decimal will make that last 0 a significant figure. And the final portion of our test for Unit 1 will be over the practice problems that we did last week using dimensional analysis. Now, dimensional analysis, as just a review question or a concept review, is that this allows us to go between different units, and it allows us to actually see the cancellation of units. And so our final step of any problem would be that we would have one unit that would be still present, not canceled from the math that you've just done. Okay? Typically, dimensional analysis is written out in a straight line, step by step, until you get an answer. And in this answer, we would want to include the units and the proper number of significant figures. Okay, and on the next couple slides, we'll do a few examples using our metric conversions and using the process of dimensional analysis to get us to a final answer. So problem 1, let's go ahead and let's go from our base unit. So let's say 7.5 grams. Grams is a base unit, and we want to convert that to milligrams. Milligrams is a small m and a little g. We have to ask ourselves first, how do we cancel grams to get to milligrams? Since we're already at the base unit, this is only a one-step problem. And if we want to cancel grams, grams go on the bottom, which means that milligrams go on top. The second question we need to ask ourselves is, which is bigger, a gram or a milligram? Okay, since grams are the base unit and our milligrams were below, the gram is bigger. So we say, in 1 gram, how many milligrams are there? And the prefix milli means 1,000. So it takes a lot of milligrams to equal 1 gram. Our units would cancel. We're left with milligrams. So what we would do here would be 7.5 7.5 times 1,000, and we would get our answer here in milligrams because it is the only unit that's still left and has not been canceled. Okay, problem 2, let's go an extra step and make it just a little bit more complicated. 0.152 milliliters, and let's try to get that into kiloliters. Okay, so we need to ask ourselves the questions. What does the prefix milli mean? And is it larger than or smaller than the base unit? The base unit in this case is the liter. And then, what does the prefix kilo mean? And is a kiloliter bigger than or smaller than the base unit? Okay, so with those initial questions, I'll go ahead and I'll start filling in the problem. Step number 1 is we want to cancel milliliters. So we put milliliters on the bottom. The rule is we always go back to base. So the liter is our base unit. Now what we saw in the problem earlier, the problem above, milli is smaller than the base unit. So in one base unit, there are 1,000 or 10 to the third milliliters in 1 liter. Milliliters would cancel, and step 2 would be converting our liters, our base unit, to kiloliters because that's what we're trying to find. So, liters need to be canceled, they go on bottom. We're solving for kiloliters, they go on top. And again, we ask ourselves the question, which is bigger, a kiloliter or a liter? And the answer is a kiloliter. In 1 kiloliter, there are 1,000 liters. Our liters cancel, and to solve this problem now, here's what we do. We take 0.152 divided by 1,000 divided by 1,000, and our answer goes here. The only units that we haven't canceled are kiloliters, and that's because we're trying to find kiloliters. Our final answer should have 3 significant figures. And if we enter that in the calculator correctly, we should come up with the correct answer.